Hi, today we're going to talk about a concept called the independence of x and y. We have a single goal for this session. It's such an important idea that we're going to focus the whole session on this one idea, that motion in one direction is independent of motion in a perpendicular direction. The first direction we might call the x direction, the other direction we might call the y direction. So this is why we shorten this down, this concept, to call it the independence of x and y. The independence of motion in each of two different directions. Now, much like a lot of other things we do, this idea has some limitations. It is very powerful, but we have to apply it where it's appropriate, as usual. So, a situation in which it would not apply is a situation where air resistance is important. Now, most of the time, we're going to neglect air resistance, and so we will be able to use this powerful concept that what happens in one direction is independent of what happens in a perpendicular direction, the independence of x and y. Okay, so we will apply this idea to a particular example. So first we're going to take a ball and we'll simply let it go from rest. And it's a height h above the ground, so once we let it go, gravity takes over and it accelerates the ball down toward the ground. We then take a second ball and we're going to release this one at the same time as the first one, but this one has an initial velocity that is entirely horizontal. It gets released from the same height as the first ball, and the question is simply which ball lands on the ground first. And we will neglect air resistance. So let's just have a look at these two motions, just so we know what we're trying to compare. So the first motion is this motion of the ball, which is simply dropped from rest. So it falls, in this case, 20 meters down to the ground. The other ball has an initial velocity directed horizontal and follows this particular path down to the ground. It also falls through a height of 20 meters. So, which ball lands on the ground first? Well, there's some possible answers. The first ball, the one that simply goes straight down. The second ball, the one that follows this interesting curved trajectory. Or a third answer is both hit the ground at the same time. So, take a few seconds and consider the different answers and see which one appeals to you best. Okay, we're going to analyze these different motions and see what we think. So what we're going to do first is draw a motion diagram for ball number one. Okay, so here we go. We're dropping ball number one, and we can see what it does. And we also recognize this motion diagram. We have seen this before. What we see is the images of the ball, which are left behind at equal time intervals, are spaced farther and farther and farther apart as the ball falls down to the ground. And that is totally consistent with motion with constant acceleration. Does this ball experience constant acceleration? Would we expect that? Sure. Once we let it go, then the only force acting is the downward force of gravity applied by the Earth on the ball. And that's a constant force, and therefore it gives rise to a constant acceleration. Okay, so that's something we've seen before. Let's consider now ball number two. So once again, we'll draw a motion diagram for ball number two. This is the one that has the initial velocity directed horizontal. Okay, so here goes the ball. And it's a shape we may not have seen before, but it's we're going to spend some time on analyzing this kind of shape. And this shape is actually known as a parabola. And once again, we see that even though the ball initially starts with no motion vertically, it soon acquires a vertical motion, and once again that's because of the Earth pulling on the ball via the force of gravity. Okay, so those are the two motion diagrams. Much like the other ball, the first ball, the successive images of this particular ball are left behind, or get further and further apart as time goes on, as the ball falls. Okay, so let's break this motion diagram, this one, down a little bit. Okay, so what we're going to do is we're going to break it apart into the horizontal component of the motion and the vertical component of the motion. So we'll draw basically 3 motion diagrams, the whole thing, just the vertical part and just the horizontal part, and see what we get. Okay, so those are the 3 different motion diagrams. This is all to do with this parabolic trajectory. Now the equally spaced red dots at the top are the motion diagram we get for the horizontal motion, and because these dots are equally spaced, we say, hey, we recognize that too. That is motion with constant velocity. Well, what's this constant velocity we have horizontally? Well, that's just the initial velocity that we gave the ball. So we gave the ball some initial velocity entirely directed horizontally, and there's nothing to change that because there's no horizontal forces acting on the ball. So horizontally, all it does is go across at constant velocity. Let's see what we have vertically. So vertically, we have dots that get further and further apart as the ball falls down toward the ground. Well, that looks like motion with constant acceleration, and it is. Because vertically what's going on is it has no initial velocity vertically. It's falling through a height of 20 meters, and it's got a constant force acting, constant vertical force acting down on it the whole time, and that is coming from the Earth exerting a gravitational force on the ball. And that gives rise to a constant acceleration. Okay, and if you want to know where the ball is at any instant in time, you say, well, where is it horizontally? Where is it vertically? And you can figure out exactly where it is in space. It's kind of the intersection of the horizontal motion with the vertical motion. You can do that at any instant in time, and you trace out this beautiful parabola that we see before us. Okay, so now we put everything together. We draw the motion diagram of ball 1 and ball 2 side by side, and we're splitting ball 2's motion diagram out into the horizontal and vertical pieces. And what we see is the balls hit the ground at exactly the same time, and that's really because what determines how long it takes for the ball to hit the ground is what goes on vertically. It has nothing whatsoever to do with what's going on horizontally. So this is the power of this idea of the independence of x and y. Okay? So what happens horizontally has no effect whatsoever on what's going on vertically. That's really this idea of the independence of x and y. So vertically, what's going on with the 2 balls? They're let go from the same height. They both start with no initial velocity vertically. They have exactly the same acceleration vertically, except it's the acceleration due to gravity. And so vertically, everything is identical for the 2 balls as far as their motion goes. So if we release them from rest at the same time, they have to hit the ground at the same time. And the fact that one ball has no horizontal motion and one ball does has absolutely no bearing on how long it takes for the balls to hit the ground. What's going on horizontally is completely irrelevant if we're focused on the vertical part of the motion. It's the vertical part of the motion that determines the time. Okay? Okay, so that situation really illustrated this very powerful idea that the vertical motion happens completely independently of the horizontal motion, the independence of x and y. And we're going to do this a lot. We're going to break down motions into 2 components, one component perpendicular to the other, and try and understand them. You know, understanding the parabola all at once is kind of tricky, but breaking it down into a constant velocity piece and a constant acceleration piece, well, we've done now those motions before. We totally understand them, so we can make sense now out of this parabola. And in general, it's not just horizontal and vertical where it applies. For instance, if we have something going down a ramp, and then some part of the motion is perpendicular to the ramp, then we can split the motion up into the 2 components parallel to the ramp, perpendicular to the ramp, and those motions are in general independent of one another. Okay, so we're going to break up a 2-dimensional problem into 2 independent 1-dimensional problems, and we can solve the 1-dimensional problems easily. And so Therefore, we can solve a lot about two-dimensional problems. Okay, so that is it for today.